So thank you for allowing me to give this presentation on this recent work that just got accepted in SciPost published in SciPost a couple of weeks back. But this is something that took a long time. So I have actually given this talk on this in a couple of previous conferences. So if anybody is there who has already listened to this, I apologize. But I think there is enough people who have not listened to this. So the idea is, okay, and the relation to this conference, okay, this is not hydrodynamics, but of course hydrodynamics is also related to concepts of thermalization and other stuff, and quantum noises and so on. So thermalization is okay. Common experience is that a system kept in contact with surroundings at a given temperature eventually thermalizes to that temperature, and this basically forms the basis of standard thermodynamics and statistical physics that we know. And yet, how such a process can consistently arise from quantum mechanics has been one of the fundamental questions with a long history in both physics and maths. And out of the long history, I mean, two approaches have kind of become standard, which is one based on open quantum systems, so I'll call OQS. Another is based on, based on isolated quantum systems. And essentially, the most popular is this eigenstate thermalization hypothesis. These two things have kind of become popular. And the question that we want to ask and answer is that in what sense are the two approaches fundamentally different, if at all, and in what physical situation their differences can be clearly demonstrated. Okay, and just I want to make this comment that the definition of thermalization actually in both of this is kind of same, that some subsystem state is basically a marginal of a global Gibbs state. So e to the power beta h of the full Hamiltonian, and trace over all the parts except for the subsystem, and the state that you get, that is the state of the subsystem. So this is the definition of thermalization from both approaches actually. Yeah. So this is the open quantum systems approach. You have a system coupled to bath. The system is in some arbitrary state. The bath is actually already in thermal state. Okay, it's already in some thermal state with some HB. And now you do the time evolution and trace out the bath. So you get the state of the system. And then so I have taken a bath, you can think of it as a lattice with a finite number of sites there. But if you take the number of sites to infinity first, and then you take t to infinity. So, this order of limits is very important. If you take this, then you end up with this as the state of the system. Okay, so this e to the power beta h, where h is the full Hamiltonian, and then LB goes to infinity, trace over bath, that is the state of the system. If this happens, then you say, okay, my system is thermalized. And this can be proven for free fermions and bosons. This is one work. There are a few more works on this. But there's no, as to my understanding, there is no mathematical proof for this when you have many body interactions in the system part, even, right? But it is believed to hold more generally, right? And then there is this isolated quantum systems approach, which is essentially the same, but just you think of this whole thing as an isolated system. And you also think of this whole thing as some non-integrable Hamiltonian. And instead of starting with a state like this, you start with some generic, it can be even pure state, which is peaked around some energy, and then you just do time evolution. And then what you look at is expectation value of some observable, some local observable. It can be of the system part or of the bath part. And then you do this time average. And that is given by something like this. So if A is on the system part, then it is given by the trace of this state, plus some order 1 by LB corrections can be there. And the fluctuation, so this is like some kind of variance in time of this quantity in some sense, and that decays exponentially with the number of sites in the system. right? If these two things happen, then it is said to be thermalized in this isolated quantum systems approach. And this is actually, it's just opposite. It definitely does not hold for free fermions and bosons, right? But it holds for non-integrable systems. So what is the difference between these two things? So I would like to just at this point, just straight away point out that there is an order of limits here. And here the order of limits is kind of a little bit different. I have taken t to infinity already, but there is an order 1 by LB correction, which means LB is still finite. So in some sense, I'm changing the order of limits. And that's basically a difference, as we will see as we go on. Okay, so how can we see this? So one way to see or understand the difference or the similarities is to take a system where we can do both. So this is the system. So I just have a chain, which is just a nearest neighbor tight binding chain with hopping. Everything is fermionic. And only between the first two sides, there can or may not be a many-body interaction, right? We'll do both the cases, right? This V is just here. And there is this hopping is gamma, this hopping is. So this is usual in our open quantum system things, is we call a double quantum dot coupled to a fermionic lead, right? And but this thing, we start from this initial state. So this is what initial state, okay, this A and B are some IID random numbers taken from standard normal distribution. This is some basis, which can be the computational basis. And we multiply by this e to the power beta h in E, where h in E is this. So h in E is h S in E plus HB is the actual Bath Hamiltonian, where this guy is chosen like this. So this is only done because essentially almost any state of two fermionic sites you can write like this. You can randomly choose these parameters that will give you an arbitrary initial state of the system. So you start with this state, you evolve, and then you look for thermalization of the double quantum dot only, right? And how can you look for it? So again, the density matrix of two fermionic sites, you can write it in terms of these four expectation values, and these four expectation values you calculate, and you construct a density matrix, see if it is close to the expected density matrix. So I just want to mention one point that this model is not also just any arbitrary kind of a model. That is, this is in quantum impurity physics, it's sometimes called this interacting resonant level model. This is just one paper. There are many papers on this. And recently, this kind of interacting resonant level model was controllably realized in experiment in this paper. Okay, so this is the setup. Now, why are we taking this initial state, right? So, this is this initial state satisfies both the requirements for this OQH and kind of ETH or IQS, like isolated quantum system thermalization, in the sense that, okay, so this is this idea of dynamical typicality. So if you take a state like this, and then you calculate, some expectation value of A on this state, that is, and you average over all possible A and B. So that is identically same as calculating trace over rho, where rho is this guy, okay? And this sample to sample fluctuations that we'll have will scale as 1 by rho square. So what we can do is, we take this. So if you now construct this R dagger for this guy, it's nothing but this Hamiltonian, which is exactly as required for the open quantum system initial condition, because the bath is like e to the power minus beta h, and system is some arbitrary initial state. And if beta is not too large, then sample to sample fluctuations will be very small. So we can just start with this and do the evolution. And this is exactly the open quantum systems situation. And for the isolated quantum system, what we need is that this state is peaked around a particular energy, which is also true if you can just check that if you do this, this thing will be satisfied. So when you do the dynamics with this initial state of that particular setup, we should be able to see thermalization in both ways. So if we want to see, if the idea that, okay, if we can see thermalization in both ways, then we have a little bit of a conundrum here, which is that expectation from open quantum system is that this thermalizes for both V equals 0 and V not equals 0. An expectation from ETH or isolated quantum system is that this thermalizes only for V not equal to 0 and does not thermalize for V equals 0, which is just free fermions. And for that, this Hamiltonian has to be non-integrable. So this is just, one side we have put the V, and such single impurity can actually make things non-integrable. As look, that was not done in this model, but single impurity can make things non-integrable, as given in these papers and some more papers also. So the question is, which is correct? The idea, okay. Now if you think about it, you'll see that there are two different regimes to this. So first, open quantum system regime is when the LB is essentially infinity, and then you have this, if you can replace this bath with this bath spectral function, that is exact. But if you start this system, so it's like I have this, and this is just a bath in some thermal state in the open quantum systems language, and this coupling is not there initially. Now I switch this on. So this disturbance of switching this on is going to spread in this lattice with some finite speed, which is this given by this Lieb-Robinson bounds. So I can kind of figure out some, some open quantum system time scale in the sense that before this time scale, this dynamics is going to be identical as compared with this LB going to infinity, right? So I have a finite bath, but before this time scale, this double quantum dot does not know that the bath is finite. Okay, so this is the open quantum systems regime. And if we are, so L naught is some, it's some arbitrary shift, but it's a finite thing. It's, you can figure it out numerically to your accuracy of your liking, but yeah, but it's something finite. And, and the expectation from open quantum system is both for V equals 0 and not equals 0. This, if you look at in this regime, things should thermalize, but you have to only look at in this regime. And isolated quantum system is basically everything else. And in that regime, you might expect this to happen, but this should only happen for the interacting one, for V not equals 0. Okay, so that is the thing. And just one word about the numerical technique. So we just need to have long enough time and large enough systems and so on. So you use this Chebyshev polynomial method along with. So this is basically all the simulations that are essentially numerically exact for the time evolution. There are other slight sources of error which we will discuss later. And if you want to calculate you have to compare with this, the global Gibbs state, and then trace over this thing. That also you can calculate by imaginary time evolution using the same. Okay, so what is the answer? This is the answer, and this is what you see, right? So what you see is that, okay, I'm plotting one of these observables. We can plot any other. All of these will have similar behavior. So this is free fermions with V equals 0. So this is the model again, and this is the initial state, right? And this is the time scale, which is this, right? And I have given it for the smallest one, essentially. Okay, so now what you see is, this is a time scale where whatever bath size you take, all of them fall on top of each other. So in this case, this double quantum dot does not know that the bath is finite. All of them fall on top of each other. And this is the dashed line is the thermal value, and it reaches the thermal value, right? This is a different initial state. This is a different initial state. Whatever initial state you start with, you reach that value. Perfect thermalization. Same thing in this regime for V equals not equals 0. V by G equals 1, right? That is perfectly fine. Outside this regime, you can see that different LB have different plots, which means that the double quantum dot knows that the bath is finite. This is also true. But with V by G equals 0, you just see it go into some kind of very, something that looks like a whole lot of noise, but probably is not. But with V equals 1, there is no such thing essentially. All these fluctuations are just suppressed. And I just want to again emphasize that V is only here and everything else is non-interactive, right? It's only in this system, right? And you see this. And now the point is, if you take these, some late time things, and you try to extract some scalings and see how this fluctuation scale and this scale and so on, you will see the isolated quantum system thermalization behavior. And that occurs only for V by G equals 1. So that is the main thing. The rest of the things are just looking at these things in a bit more detail. So first part is this OQS regime, which is kind of simple. So just it is the same plot, just zoomed in, only in this regime, right? It is the same plot, right? And what you see is just for various LBs, it just follows the same curve until it just reaches this value. Right? You start with two different initial conditions, you reach the same value. Perfect. You take the state of the double quantum dot and compare with what you expect from the thermal thing. This is the trace distance at time T OQS, where T OQS is this, and you plot it versus LB because T OQS also depends on LB, and you see that the trace distance decays exponentially with LB. Perfect thermalization. Same thing occurs for V equals 1. Is as expected from open quantum system thermalization. Now is the same plot here, just x-axis will now we will look at when the x-axis is just in linear scale instead of log scale. Okay, the plot looks like this. So it just looks like noise when you have V by G is equal to 0. But when V by G is equal to 1, you see that things are tending to fall into some kind of fluctuation, small fluctuations about some smooth curve, right? And then you do what? You want to characterize the fluctuations. So what we do is something like this. We take some value of T1 and just calculate the variance of the data points, okay, from T1 to the last point. And then we make a plot versus T1. So what you see is as we keep on kind of shifting T1, this thing kind of saturates to some plateau, right? And but if you do it for a larger bath size, it saturates to a plateau in a later time and also a smaller value. If you do it for a larger, it saturates to a later time and again a smaller value. And this y-axis is log, so this decay is essentially exponential. So if we just look at, let's say here, these many things, and if you make a plot, and you can do the plot for all the 4 observables of the double quantum dot, you see that the fluctuations decay exponentially with LB. So this holds as expected for isolated quantum system thermalization. And the last thing to check is whether this holds. This is the expectation value minus what is expected from thermal state. This should go as 1 by LB, or even higher powers are fine, but we find 1 by LB, and you see that we make a plot with 1 by LB, fit 1 by LB minus some small values. Now these small values, we think we have good reason to believe that this is coming from numerical limitations. Of course, if you look at these plots, things are not completely relaxed. It's still going down and so on. So if we could go to, it's still a very, very, very hard numerical calculation to go up to this with many body interactions and so on. But if we could go on like up to here, let's say, we probably, those small values will be gone. And in principle, we are not averaging over various initial states. That also might have some small errors. So I think that the small value is just numerical. But you see that overall, the main thing is 1 by LB or each of these observables. And if you take the trace distance, it's also just 1 by LB and some small value. So so we have thermalization in the isolated quantum system sense when T is greater than T OQS, in which case only when V is not equal to 0, things thermalize as expected, because V equal to 0 is free Fermions. In less than, so when T is less than T OQS, then both free Fermions and isolated system and with V not equals 0, both of them essentially thermalize as expected from OQS. So what is the main thing that is different? The time scales and the length scales. And what is the main thing that is different? It is the order of limits. What is T OQS? Before the system, the double quantum dot could feel that the bath is finite. So that is the limit where LB is basically going to infinity first, and then T is going to infinity. What is this thing? This thing has already seen that the bath is finite, and then it is fluctuating. So here, we are first taking kind of T to infinity because we are kind of averaging over T. And then we are taking LB to infinity. So this thermalization in the sense of open quantum systems and thermalization in the sense of isolated quantum systems are kind of related by a switching in order of limits of thermodynamic limit and long time limit. That is the main thing. Now the final thing is, this whole thing, is it non-integrable? So, okay, we did a lot of things to just check. So we did calculated spectral form factor, which is this guy. We calculated spacing distribution. We calculated the mean value of this nearest neighbor spacings. All of these things are used to characterize whether things are non-integrable or not. And this spacing distribution should have some universal ramp and plateau behavior given by this function for non-integrable systems. And now I'm introducing something called a Brody distribution, which is not always introduced for this spacing distribution. But if you put a equals 0, you get the Poisson distribution, and it is integrable. And the value of r is 2 log 2 minus 1. And if you put a equals 1, then you get this Wigner-Dyson distribution, and the value of r is this con. So these are all that are used to usually distinguish between what is integrable and what is non-integrable numerically. And what we see is something kind of interesting, is that, okay, v equals 0, okay, something happens, that is all fine. V equals 1, it seems to follow that thing much better than this, definitely, but there are still a lot of fluctuations. And when you plot the spacing distribution, you see that, okay, v equals 0 is fine, it's the Poisson distribution, but with v equals 1, you don't get the Wigner-Dyson completely, you get a Brody distribution with a value of a, which is in between 0 and 1. Right? And just to make sure that things are not happening from some numerical errors and so on, we did one more, this r and so on, and even versus v. And what we see is that if you fit this a, it goes from 0 here, and it never goes to 1. It goes to something in between, and just remains in between. And if you do this r, this is the value for Poisson distribution, this is the value for Wigner-Dyson. It also just, it's the same behavior from both things. Right? But this is, of course, calculated with exact diagonalization and finding the eigenvalues. So this is with, the bath sizes or the system sizes are much smaller than what could be done for the dynamics. So, okay, nothing rules out that this is a finite size effect or not, but clearly this is something in between. And v equals 1 is just here. So, okay, maybe it's finite size, but maybe it's not. Point is, this thing is what for lack of a better word, we have called it partially non-integrable. Like this has one non-integrable feature, which is level repulsion. This is 0 here, but this is not fully Wigner-Dyson. But we have seen that this thing, we have just seen that this thing is perfectly showing thermalization. Right? So yeah, so this is all we have. This is the summary of the full set of results that we had. So we started with this kind of a Hamiltonian, where this is the only thing that has the many-body interaction. We start with this initial state, and if we start with this initial state, in the same dynamics, we see two different regimes. One regime corresponds to thermal, like open quantum system. One regime corresponds to isolated quantum system. And we see thermalization in the open quantum system regime in the open quantum sense, which occurs both for free fermions and for v not equals 0. And in this regime, we find thermalization in the isolated quantum sense, isolated quantum system sense, where it is known that free fermions will not thermalize in the same sense. And if it is not free fermions and you have some non-integrable behavior, then things are supposed to thermalize. And the point is, we did not find fully non-integrable behavior. This system has level repulsion, but not completely sure that it has Wigner-Dyson distribution. So maybe the whole point is not required. Maybe level repulsion is enough to guarantee thermalization. We don't know. We'll leave you with those questions. And of course, this is just one work. You can explore other models. You can look at the case where the bath itself has some integrability. Here, the bath was just free fermions. And we can think of, if you think of in the open quantum system sense, you can think of what is the non-Markovian behavior in the late time case and so on. And these are some other works which are very loosely related, but related with some kind of thermalization. And yeah, these are the set of works, from Lindbladians and so on. And yeah, thank you.
Thank you very much. Is there any?
Yes, so you mentioned that the thermalization in both the cases, it's in some sense dependent on the kind of initial state you take. So if I take an initial state which is still sharply peaked around some energy, so that the condition for ETH is satisfied, and I'm working in the non-integrable case, but your initial state is not thermal on the bath side. So in that case, how would the situation differ?
I don't know. And I mean, those are all very interesting questions. This was specifically designed to be able to see both kinds of thermalization in the same dynamics.
In the same dynamics.
Right? And that's something kind of interesting. To make a proper comparison, you have to kind of do this, but these are all interesting questions to look at.
Yeah, so would it be at least safe to say that if the bath doesn't start in the thermal initial state, then the thermalization will only happen in the ETH sense?
I don't know. And it probably also has to do with if the bath Hamiltonian is non-integrable or not. If the bath Hamiltonian is non-integrable, probably you don't even have to start with a.
Yeah. But in this case.
In this case, maybe we have to try.
Sure. Thanks.
Is there any other question? Okay, maybe I can ask one question. So could you go back to the slide where you showed the spectral form factor?
Yeah.
So the right, the B, is it, this is for the isolated case, right?
No. So isolated means is this Hamiltonian, and there's no isolated. We are always just evolving this Hamiltonian. There's no other things, right?
Okay.
And the whole thing is like this whole Hamiltonian. You can think of this as the bath.
Oh,
if the system does not see that the bath is finite, and that is up to a finite time.
Okay.
And so there are two time regimes.
Right. So it's not like you're dealing with open systems.
No.
See. And then this the ramp kicks in over the time scale controlled by the Taurus time. Right?
Yeah, that will be the Taurus time.
But that's different from the kind of time scale you see in the distinction between the isolated and the open.
Yeah, that is very different because I think that is different because okay, but difference by what we have not completely analyzed. Okay, because to do the dynamics, we can do up to much larger systems. Now to calculate this, actually we have to kind of diagonalize and this up to much smaller systems. So it's kind of hard to completely compare.
Any further question? Okay, if not, let's thank the speaker again.
Thank you.